All right, this go around we get to talk about graphing rational functions. So I guess really the first thing we need to talk about is what in the world is a rational function? What is rational fancy talk for in math? Fractions, right on. So we get the amazing opportunity here to work with some fractions. So that's cool. All right, so here's an example of a rational function. Now notice this is a fraction, but the biggest deal whenever comes to a rational function is the fact that your x is in the denominator. Now, let's think back to when we were talking domain. What were our two big fat no-nos whenever it comes to domain? Yep, you can't have a 0 in the denominator. Awesome. And what was the other one? Just, for fun. Negative under a radical. Good. So our two big fat no-nos is you can't have a 0 in the denominator and a negative under the radical. Now right now the radical doesn't affect us, but that 0 in the denominator does. So if I actually wanted to find the domain of this function, what is going to make my denominator 0? Well, set it equal to 0. Good. So if I want to say when is x minus 2 equal to 0, I'm going to set that equal to 0. And I know it happens when x equals 2. So that means my domain can be anything at all except it cannot equal 2. So how do we write that for a domain? From negative infinity up to 2, parenthesis or bracket, parenthesis good because it's not including, union with 2 to infinity. Excellent. So basically, domain is from negative infinity to positive infinity always. Then if you have something that's messed up or a big fat no-no that's associated with that, then we have to break up that negative to positive infinity. And in this instance, it can't be 2, so I'm breaking up that negative to positive infinity at 2. So I can go up to 2, but not including, then pick back up again and take off. So good. That's important when we start talking about rational functions. So think about that in my domain. That means I cannot have an x value at 2. If it's not in the domain, we're out. All right, check this out. Okay, just like in that last section when we graphed polynomials, the end behavior drove the function. And when we graph rational functions, our asymptotes are going to drive the function. So, in order to figure out what's going to be driving my function, I kind of need to know what an asymptote is. Well, here it is. An asymptote is an imaginary line that your graph approaches but may not cross. Now, I want to draw you to the fact that it says may not cross. Like any good rule, there is an exception. And for this one, there is one exception to the rule. And we'll talk about it when we get there. It's with horizontal. But majority of the time, you cannot cross. There is one exception for an asymptote. So just think about an asymptote. Your graph is drawn toward that asymptote. It's an imaginary line that your graph approaches. It's drawn toward it, but it does not cross. Cool. Let's check this out. All right, the first asymptote we're going to talk about is a vertical asymptote. And a vertical asymptote is a brick wall. There is nothing getting through this vertical asymptote. That means it's something that can never be interrupted. That is when the denominator equals 0. Da-da-da-da-da-da. So remember how we just talked about not having a value in the domain when your denominator equals 0, that's not part of the domain. When you have a rational function here, that is where you have a vertical asymptote. So remember, it's an imaginary line that your graph approaches but may not cross. So when your denominator is 0, that is where you have a vertical asymptote. That's why it is a brick wall. It will never cross a vertical asymptote. Cool, let's do. So an example of a vertical asymptote would be something like y is equal to, let's just use the same one, 5, over x minus 2. So if we're just going to do a quick little graph on this, just ghetto graph this a little bit here, just so we have an example. then I know that I have a vertical asymptote at x equals 2. Now remember, this is a vertical line. The equation of a vertical line is x equals some number. So if I want to find my vertical asymptote at that value, I'm going to go over to 2, and I'm going to make a dashed line. And that is my vertical asymptote. All right, that's it. So I just have a vertical asymptote. I'm not really sure at this point what the rest of my graph does, but it approaches and does not cross. Okay, let's look at some other types of asymptotes. Okay, our next two types of asymptotes is either a horizontal asymptote or a slant or oblique. Slant and oblique are the same thing, just depends on who you're talking to and what book you're looking at is the word that's used, but they mean the same thing, slant or oblique asymptote. In order to find either one of these, we have to look at your lead behavior. Kind of like with the polynomials, in order to find the end behavior of the polynomial, you looked at the leading coefficient and the highest degree. That's the same concept. You always look at the leading behavior. We're going to look at the leading behavior of the numerator and denominator, and that is going to tell us what our asymptotes is. Okay, here's our first scenario. Okay, check this out. When the degree of the numerator is smaller than the degree of the denominator, you get a horizontal asymptote at y equals 0. So what is the degree again? Your highest exponent, yes. So the highest exponent of the numerator is smaller than the highest exponent of the denominator. It's automatically a horizontal asymptote at y equals 0. Now, what is that? So if I have a horizontal asymptote at y equals 0, where is that actually? The x-axis, yes. So that basically means I have a horizontal asymptote along the x-axis. For example, if we have something like y is equal to x minus 2 over x squared plus 1 or some crap, anything. As long as the degree on the top is smaller than the bottom and 1 is smaller than 2, I have an automatic horizontal asymptote at y equals 0. Cool. Okay. Nice. So I know so far the numerator is smaller than the denominator, automatic y equals 0. Cool. Let's check out a second scenario. Okay, here's our second scenario. When the degree of the numerator is the same as the degree of the denominator, then you have a horizontal asymptote at the leading coefficients. Now let's think about that for a second. Our first scenario was, it was smaller on top, automatic horizontal asymptote at y equals 0. This one is if they are the same. Then you have a horizontal asymptote at the leading coefficients. So let's look and see what that looks like. So here's an example. If I were to have, I don't know, y is equal to 3x plus 6 over 2x minus 1 or some crap, I don't know. So if I'm looking at this, the x's are the same. That means my horizontal asymptote is at the leading coefficients. So I have a horizontal asymptote at y is equal to 3/2. All right, so whatever your leading coefficient is, that's where your horizontal asymptote is. And it doesn't have to be both numbers. For instance, you could have y is equal to 2x squared minus 1 over x squared plus 6 or something. You still have an x squared on both of those cases, but your horizontal asymptote here is just going to be y equals 2 because 2 over 1 is just 2. Pretty cool, huh? All right, let's look at our third and final scenario. I bet you can't guess what that is. Okay, so now we have seen where the degree in the numerator is less than the degree in the denominator, giving me a horizontal asymptote at y equals 0. We have seen where the degrees are the same, so a horizontal asymptote at the coefficients. Now, our third scenario is when the degree in the numerator is specifically 1 degree more, just one more than the denominator. Then you have a slant asymptote. Now, I typically call it a slant asymptote. Sometimes I call it oblique, which means the same thing as slant. So we're really saying the same thing. It just depends on how you learned it and what it was called. So this is what that looks like. So for example, if I have, I don't know, f of x is equal to x squared plus 2x minus 1 over x plus 6. So notice I have a squared in the numerator and just an x in the denominator. So I have 1 degree higher in the numerator with that 2 than in the denominator, because if x doesn't have anything, it's an automatic 1. So in this case, you do a division. And anytime you see a denominator like x plus 6, you know you can use synthetic division. So I'm going to put a negative 6 in front. Then we're going to write our coefficients, 1, 2, and negative 1. I got a little overzealous with that line, didn't I? Okay, so drop down the 1. Negative 6 times 1 is negative 6, giving me a negative 4. Positive 24 is 23. Now here's the deal whenever it comes to this. This is called a slant asymptote or an oblique asymptote because this is actually a line with a slope. So it will be slant. So a line with a slope is slant here. Now we're looking at, okay, now the kicker whenever it comes to these is no one cares about the remainder. You want your first term and your second term because y is equal to a 1x minus 4. So your first term here is your slope and your second term is your y-intercept. So that is your slant asymptote. Pretty cool, right? Cool. Let's do some examples and kind of feel these things out here a little bit.